materials. We learned that materials that, are attracted to magnets, we call them ferromagnetic, but let's look at some other options here, okay? Remember, for a material to be attracted to a magnet, to be responding to a magnet, it itself has to be a magnetic dipole. It has to be made out of materials that have magnetic dipoles. So we say that materials that are non-magnetic, don't have magnetic dipoles, or can't create magnetic domains, whatever the problem is, we call them just non-magnetic, okay? Completely unaffected by magnets, couldn't care less, okay? Wood and rubber are fantastic examples of that. Some materials are slightly attracted to strong magnets. For example, oxygen and sodium. Oxygen's easy. I don't know if you know how oxygen gets around your body. Maybe you do. How does oxygen get around your body?
Blood.
In your blood. What part of your blood carries oxygen?
Veins.
No. What part of are your veins your blood?
No.
Right. It's like the highway is not your car, right? I'm not being a smartass. I'm just making sure we are okay. Good. So
like energy or.
So what part of your what parts of blood are there? You got it right. But you're right. But hang on a second. You're doing great. What parts of blood are there? What's in blood? Cells and plasma. Okay. The blood cells. What kind of blood cells do we have? Red cells, white cells, and platelets. Right. 3 types of blood cells. Right. Erythrocytes, leukocytes, thrombocytes. Okay. Which of those 3 carries oxygen? Red cells carry oxygen. Okay, I'll help explain that more in a second. But okay, so red cells, white cells, platelets. Red cells carry oxygen. And Michael, what's in red blood cells that carries the oxygen? Hemoglobin. Okay, so picture this: in every cubic millimeter of blood, there's something like 5 million or so red blood cells, okay? 5 million in every cubic millimeter, that much, okay? So every one of those red blood cells is absolutely packed to the gills with molecules called hemoglobin. Every red blood cell has 250 million hemoglobin molecules in it, okay? So lots of hemoglobin, okay? Lots of hemoglobin, lots of red blood cells. Hemoglobin has the property that it's a blood protein that carries and holds on to and built in as part of it iron. Okay, iron is part of hemoglobin. Okay, iron is ferromagnetic. Okay, iron is a magnetic dipole. Okay. Iron in here is a magnetic dipole, okay? Oxygen is paramagnetic, okay? Oxygen is kind of attracted to magnets, okay? So, hemoglobin can hold on to oxygen because of this property, okay? But not like latched on, never gonna let go, right? Held on to slightly, let's say, okay? So oxygen can move around in your red blood cells and be moved around your body and then hop off of the hemoglobin molecule when it gets to areas that have less oxygen saturation, and it does that by simple diffusion. The point is that your red blood cells have iron. Iron does this thing where it can attract and hold on to oxygen, okay? So because of that, oxygen can move around your body. And we need oxygen, right? It's super important for our cells to work. So oxygen's paramagnetic, slightly attracted. So notice what they say for paramagnetic. Oxygen has a magnetic dipole, is a magnetic dipole, but does not form magnetic domains. And there's a complicated reason why that I won't even bother trying to go into, because I wouldn't be able to do it very well, do justice to that. But we can say that it doesn't form domains, okay? Ferromagnetic materials, strongly attracted, do form magnetic domains. Ferro, in this case, is a root meaning iron, or fire, but we use ferro. And in fact, if you look on the periodic table, iron is listed as Fe for ferro. Okay. And lastly, diamagnetic. Diamagnetic materials are repelled. Glass and water are an example that repel magnetic fields. So magnetic field would either have to go around glass, right, or not penetrate at all. Glass does not let glass disturbs magnetic fields. Okay, it interrupts the magnetic field. Okay, so glass and water are examples of that. Okay, let's talk about electromagnets, magnetic fields for a moment, and then we'll move on. And I want to try to get out the laws of magnetism here in a sec. So, electromagnets, okay? Remember, moving electric charges generate a magnetic field. Okay, the thing I haven't told you yet is that the magnetic field will move in a direction perpendicular to the direction the electric field is running. So the electric field runs one direction, the magnetic field always points perpendicular to that. Shown here, in this coil of wire, current runs in one end, down through the wire as the wire coils and out the other end. So the direction of current is, let's say, up and down. Okay.
So it won't run along the wire?
No, it blooms away from the wire.
No, I'm saying so you're saying the current is coming in through the wire.
Yes.
But then the current runs straight down, but not through the wire. It runs straight down the center.
No, the electric current is running in circles through the wire like that. Okay. Right? But the overall direction of travel is vertical in this on the screen. Yeah, it does. The electricity does run through the wire itself, though. Yeah, more correctly on the surface of the wire, but don't worry about that. Same thing. When you insert a rod, a ferrous material, a rod of ferrous material like iron in through the middle, or as Sydney told us earlier, you take a nail and wrap a coil of wire tightly around the nail, right? Then you are now strengthening that magnetic field by having that ferrous material present. So you develop a magnetic north and a magnetic south pole, much like the Earth has a magnetic north and south pole, and like any regular, natural magnet has a north and south pole. The thing about electromagnets are, they only work as long as electric current is running through them, okay? The magnetic field is proportional to the quantity of electric current. Right now we're assuming the electric current is just consistent, but it's proportional to quantity. If the electric current is stronger, the magnetic field is stronger. Okay, this is why a magnet that picks up cars has to use just a lot more power than the magnet that picks up, screws, for example. Right? The electric current is proportional to the magnetic field amplitude. Here's a representation of a magnetic field so you can see it. Okay, this is just a ferrous material, a ferromagnetic material here. There's a magnet, a magnetized material with a bunch of ferromagnetic filings, like shavings, iron shavings, suspended in oil. Okay, so it's a blocky box thing filled with oil, and in the middle they've suspended a magnet. Okay, magnetic bar. That bar has a north pole and a south pole, and now you can see that those iron filings have traced out, right, the shape of that magnetic field. Okay, magnetic lines of force flow outward from the north pole and inward to the south pole. Okay, so there really is a direction out from the north into the south.
Do they move, or do they stay in that position?
The field?
Yeah, so say like in that picture.
They're going to hang out right there.
They're always just going to be in the exact same.
Yeah, so if you're asking like what do the iron filings do? Yeah, so they're not all going to be dragged in the north pole. They're going to spread out equally along. Remember, each little iron filing is its own little magnet, and so they're going to be spaced apart equally. The magnetic field is weakest out here and strongest up here towards the poles, which is why you see the concentration here at the poles.
What is that called? Like the object. I'm looking on Amazon.
To buy one? So you can buy, there are things called ferrofluid that you can buy. That's not what this is. What do we want to name this? What do we name it?